From the Tower of Babel and Jacob's Ladder to the 20th century space race, we have attempted to reach the heavens. Humanity has gazed up at the stars and fantasized about conquering the cosmos. However, getting to space is difficult. No matter how much we wish it were simple and inexpensive to float out and see our little blue marble in the vast darkness, the only way to do so right now is to be an astronaut or a billionaire. However, all is not lost. The space elevator is a concept that could serve as the starting point for our exploration and spread across the stars. There are some against it.
I always think of like Charlie and the Chocolate Factory when I hear the space elevator, but because people sort of manage like an elevator, you press up and you're just like, now you're in space. This is like this is extremely complicated. I don't think it's really realistic to have a space elevator. Let me put it this way, like at the point at which we have like a bridge from LA to Tokyo, which I think is a much easier problem.
A space elevator will be humanity's first planetary-scale structure, and it will embody the remarkable concept of transformational infrastructure. Because the space elevator will lift massive cargo and deliver it daily, cheaply, safely, routinely, and in an environmentally neutral manner. Access to space via the space elevator will be a game changer. The regular use of a permanent transportation infrastructure enables new missions and changes how we imagine the future. Why not just use rockets instead? Rockets are extremely expensive. To put a payload into low Earth orbit, the shuttle costs $10,000 per pound, and going to the moon or Mars costs hundreds of thousands of dollars per pound or more. Rockets are also limited in terms of payload capacity, and they are risky. The cost of a space elevator is a fraction of that. It could be 100 or 1,000 of current costs, and there are no rocket engines that could explode. The key concept of the space elevator appeared in 1895 when Russian scientist Konstantin Tsiolkovsky was inspired by the Eiffel Tower in Paris. He considered a similar tower that reached all the way into space and was built from the ground up to the altitude of 35,786 kilometers, the height of geostationary orbit. Obayashi Corporation, one of Japan's top construction companies, is currently testing carbon nanotubes, a key element towards bringing the space elevator dream to life. The structure composed of a 96,000-kilometer carbon nanotubes cable, a 400-meter diameter floating Earth port, and a 12,500-ton counterbalance, and have the capacity to carry 100-ton climbers. Obayashi believes that the elevator will be ready in 2050 provided that carbon nanotubes become scalable by 2030. Right now we can't make the cable long enough. We can only make 3-centimeter long nanotubes, but we need much more. We think by 2030 we'll be able to do it. Building materials for the space lift will be delivered by a rocket in several stages to build a spaceship at low Earth orbit. The spaceship will use electric propulsion to move up as it circles around the Earth, reaching geostationary Earth orbit. That is where it will start to rotate at the same speed as the Earth's rotation. Once the spaceship reaches an altitude of 36,000 kilometers, it will move up while releasing the carbon nanotubes cable with thrusters attached to its tip. After 8 months from the rocket launch, the cable will reach the Earth's surface. Climber for construction goes up while attaching reinforcing cables and joins the counterweight at the top. By reinforcement about 500 times, 100-ton climber can be used. With the completed climber, materials will be carried to an altitude of 36,000 kilometers to complete the geostationary station. Earthport is a gateway to space on Earth. The Earthport is built in 2 sections, one on land at the equator and one at sea, connected by an undersea tunnel. A space elevator, in addition to being a daring feat of engineering, provides numerous advantages. For starters, the cost savings over conventional rockets would expedite plans to commercialize and even populate low Earth orbit, establish human settlements on Mars, and save billions on deep space missions. The clearest challenge is, of course, the tether that would run from the base station on Earth to the orbiting station. This tether needs to be 32,000 to 100,000 kilometers long, depending on who you ask. It requires materials that are stronger than steel, Kevlar, spider web, or anything else we currently have. At least, if we build it on Earth, not on the moon. The difficulty of construction scales with the gravity. There is hope that nanotechnology would be able to produce materials which are that strong someday. Second, there's also the matter of the titanic forces the structure will have to deal with, like wind shear, storms, and hurricanes at lower altitudes, and micrometeoroids, and the sun and moon's gravitational influence at higher altitudes. Add to that the stress of regularly sending pod cars up and down the tether, and the result could be oscillations that eventually turn violent. The challenges of building and operating a space elevator are enormous, just like the structure itself. However, given the benefits of having one, it's easy to see why it continues to attract supporters and adherents. And as the necessary technologies improve, we may find ourselves getting closer and closer to realizing it. It is not possible to build one for Earth. It may be possible to build them on other celestial bodies with lower gravity, the moon, Mars, etc. But that's another story for another time.